Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. Okay, today's topic what we see right here water masses of the oceans, with emphasis on the Atlantic Ocean. Why the Atlantic Ocean? It's a very dynamic ocean and it's a lot more exciting what goes on in the Atlantic Ocean as compared to the other major ocean basins. So, before we get going, let's discuss what is a water mass. Okay? In general terms, a water mass is a body of water in the ocean that can be found at any depth, surface layers to the abyss. It could be several hundreds of meters thick, it could be 1 or 2 kilometers thick, but they can be found at any depth in the ocean. They are typically identified by characteristic parameters, chiefly temperature and salinity. In other words, a water mass X might have a temperature range of 9 to 11 C. It might have a salinity range of 34.9 to 35.3 practical salinity units, something like that. These values often have a range associated with them, reflecting movement, mixing processes that occur and can modify these parameters. So, like the example I just gave, 9 to 11 C, 34.9 and 35.3 practical salinity units, that range there is, the water mass moving about, interacting with other water masses, having a little bit of mixing processes, and where you can entrain some of the other properties, characteristics from other water masses that will provide for these range of values. Usually, if you see what we call a single point measurement, in other words, we have this precise, temperature and this exact salinity, pretty much going to be in the middle of the water mass. So temperature and salinity combine to determine the density of the water mass. It is the small but still significant differences in temperature, salinity, and thus density that affect the movement of the water mass, namely density currents, thermohaline flow, Ekman pumping. As the water moves throughout the ocean, the different water masses come into contact with other water masses, like I was just describing, and via diffusion, double diffusion processes, mixing occurs, resulting in modified waters, the blending of the physical and also the chemical characteristics. It is common to see eddies pinch off. Now, these eddies can be on the scale of tens of kilometers to hundreds of kilometers, and smaller ones that right at interface could even be just on the order of several meters. But we typically refer to these like mesoscale eddies and so forth. Eddies play an important role in the mixing processes at all depths in the oceans, from the surface to the abyss. There are also horizontal movement of water masses. These can be induced via wind-driven stress, internal waves, which are typically found at density interfaces down in the water column. And the density interfaces are typically going to be where you might see a couple of water masses meeting up. So, to repeat the point, the subtle differences in density are sufficient to result in movement of large volumes of water throughout the ocean, which then drive the planet's climate. Now, are these movements going to be rip-roaring, fast moving? No. When you get the deeper you go, the slower the movements are going to be, but the waters are still moving. They're still transporting whatever it may be heat, oxygen, CO2, nutrients, and so forth. And these movements help drive the planet's climate. So then, how is density determined? Density of seawater is a function of temperature and salinity, unlike fresh water where only temperature determines density. Now, I have done videos on salinity. I did a video on salinity. I did a video on overturn mixing and stratification. I'll leave the links for those videos I've done that I deemed germane to this topic in the link comment below the video. So let's consider the following situations. Let's say we're going to hold salinity constant, whatever it may be. Let's say it's 35 practical salinity units. So what happens if I increase the temperature? Well, I'm holding salinity constant. I increase the temperature, so you expect the water to expand and the density decreases. And indeed, that's what happens. As you increase water temperature, the density decreases. Conversely, again, holding salinity constant, if I cool the water, water will contract and the density increases, right? So you cool down the water and then density increases. Now, in the case of fresh water, the density increases to fresh water being most dense at 4C, after which point cooling it further, the density actually then decreases. That's due to the nature of the polar covalent bonds of the hydrogen, of the water molecules with the angles of the hydrogen, oxygen atoms, and so forth. And that's why when you form ice, it floats because it's less dense than the water. Again, I refer you to my overturn mixing stratification video. Now, and going back with seawater, because of the salt content, as you getting colder and colder, you're having what's called brine rejection. So you have to reject the brine before the seawater will actually freeze. And remember, sea ice is called sea ice because the source is the sea. There's no salt in the ice itself. That's all been kicked out. So, sorry. So what if we now hold the temperature constant? Okay, I'm going to hold it at 9C. So what happens if I add more salt? Well, I increase the salinity. And the density increases. I remove the salt, again holding temperature constant. I've done what? I reduce the salinity and density decreases. Okay? In fact, when we look at forming sea ice, we're doing what? Okay, we're actually taking part of the water molecule and turning it into ice, so we're leaving less volume behind. But because of the brine rejection, the salinity has increased, which means the density has increased. And since it's at the surface, it sinks. Just like, when the Gulf Stream, becoming the northward drift in the North Atlantic, it gives off its heat, it cools down and it becomes more dense, and it sinks. Deep water formation. Okay, so now what happens when both temperature and salinity are both changing? Temperature increases, salinity increases. Temperature increases, salinity decreases. Temperature decreases, salinity decreases. Temperature decreases, salinity increases. What happens then? Hey, that's where it gets interesting. And that's where we oceanographers have a load of fun. And this is where a very important analytical tool is utilized. The TS diagram, temperature salinity diagram. And here is a typical temperature salinity diagram. Now, before we look at this graphic, look at the units here, grams per cubic centimeters. Oceanographers, look at the note over here. We express density in terms of kilograms per cubic meters. So the values here would be, instead of we're seeing 1.0255 as an example, or 1.0245, we would have it as 1,024.5 kilograms per cubic meter, etc. So basically, just move the decimal 3 spots over. But a convention we use is that we don't report the 1 and the 0. So we'll just say 24.5, 26.5. That's what we do. Now, these lines that we see here, these are called isopycnals, lines of equal density. So now let's look at this line right here sitting on the 27.5 density line. We have water parcel A, water parcel B. Now we notice, okay, the temperature for water parcel A is 0C, and it looks like that the salinity is 34.25 practical salinity units. And then as we move it over to here, we now see, reading across, that the temperature is about, looks like 9C. But yet, you say, wait a second, we made the water warmer. So wouldn't that decrease the density? But also look what happened. We increased the salinity from 34.25 to basically 35.55. So what happened here is when we increase the temperature to keep the same density, we had to increase the salinity. Conversely, if I cool the water down, like let's look at the 26.5 isopic. If I cool the water down to keep the same density, I lower the salinity. So in other words, isopycnal, especially in the TS diagram, they all tend to increase to the right, because to maintain the same density, if you increase the temperature, you increase the salinity, and vice versa. If you decrease the temperature, you also decrease the salinity to maintain the same density. So now let's say I'm going to take a temperature of 5C, and I look at the isopycnal for 26.5, and I see that my salinity is 33.5. But now I'm going to hold it at 5C, and I move across, and let's say what happens when I move it over to, say, 34.9 practical salinity units. I've increased my density, right? It went from 26.5 to 27.5 kilograms per cubic meter, right? Holding the temperature steady, increasing the salt content, increases the density. Conversely, let's take this value here of 35.65 at 0C. Okay, I'm going to hold that salinity constant, and I'm going to make the temperature warmer. And what do we see? We notice the density has decreased. Right? Went from 27.0 to 26.5. So if you want to know what's going to happen at a given temperature and what happens to the density as you change the salinity, you're going to move across horizontally to see which isopycnal gets intercepted. And if I hold a salinity constant and I change the temperature, I look up and down. I look vertically to see what the new density will be for the new temperature. This is kind of how you read these temperature salinity diagrams. And then when you have water masses mixing, well, this all gets lots of fun. And I've done some deep dive videos with you folks there where I've looked at you, explained with you some of the TS diagrams that was included in the papers. So this is, and this is what drives a lot of water movement in the oceans. These little subtle differences in density. Okay, so how is density measured? The CTD. CTD stands for conductivity, temperature, and density. Okay? Invaluable tool for oceanographers. We can't do, especially physical oceanography, without CTDs. When you write your grant and you say what equipment you use, that's like line item number one, aside from the boat. So it measures temperature as it is deployed, usually deployed vertically, and also the conductivity of the water, because salt water, oceanic water, has loads of dissolved ions in it, and these ions actually conduct electrical currents. I mean, you're not going to get zapped from it, but it does conduct electrical currents. Hence, conductivity. So the unit, the device, actually measures this conductivity. And then there's software in the unit. So then from the conductivity, the salinity is calculated. And then once the salinity is calculated, it then takes these new calculated salinity values, it takes the temperature values, it correlates it to the depth. So it's like, oh, at this depth, we have this conductivity. The software gives us this salinity at that depth, and we also have temperature at that same depth. And therefore, with the salinity just calculated, and plus the temperatures that it has recorded at that depth, we calculate the density. And usually when you download these things, you get a vertical profile, and you can get a vertical profile for the salinity, for the temperature, and the density. Okay? So CTDs are deployed vertically, typically along transects. And the diagrams and graphics, such as what we're going to look at today, are built and developed from these piles of vertical profiles that make up the transect. Okay? Today, we still use CTDs. Of course, gotten better like everything else. But a picture of the ocean is becoming more complete thanks to ROVs, Argo devices, other remote sensing equipment. In the days past, you do an oceanic cruise, you have a transect. We're going to run along this longitudinal line, or we're going to run along this latitudinal line, what have you, and you make a determination every so often, where every 100 meters, 200 meters, or what have you, whatever the the methodology is arrived at, you then drop the thing overboard, run it to as far deep as you wish. Now, it could be, typically is usually several hundred meters, depending where you're at. I mean, if you're in a small bay, well, you might be down to like 50 meters, but you get the idea. So you drop this down, you pull it up, okay, it downloads it, you go to the next station, you drop it down, and then you take all these vertical profiles and you create like a 2D and sometimes 3D picture of the shape of the ocean, the distribution of the temperature, the salinity, and the density. A lot of physical oceanography is done with CTDs and flow meters, especially for surface studies. So, here's an introduction. Now, this is diagrammatic, but we're looking at the South Pole on this side, looking at the North Pole on this side. This is for the Atlantic Ocean. Okay? We have Central Atlantic surface water, we have Antarctic intermediate water, and we have North Atlantic deep water, and then underneath it all, dive bombing off the Antarctic coast, is the Antarctic bottom water. Notice this line here delineating the barrier, or the interface between the Central Atlantic surface water and the Antarctic intermediate water. And then we have this is the Mediterranean water introducing itself here. It also curls up this way. This is basically a thermocline curling, bending up to the surface. I go into detail on my overturn mixing stratification video as to why that is, how that takes place. Again, I refer you to that video. And this is basically supposed to represent deep water formation and the sinking down to its buoyant forces, where its density is of a nature that it's denser than the Mediterranean water, denser than the Antarctic intermediate water, so it sinks below it, but it is lighter, less dense than the Antarctic bottom water, so it floats over the top of it. That's the general idea of the water mass in the Atlantic. A little more complicated, I assure you. Okay, Here's that thermocline I was just referencing in my previous slide. Okay, it comes up about 45 degrees or so south latitude, and can kind of be stretched out to 60 degrees north latitude. But this is again your central Atlantic water. Here's your intermediate water, NADW, Antarctic, North Atlantic deep water, Antarctic bottom water. So what do we see here is that with the blue, we see increasing CO2 and nutrients, but decreasing O2. So the darker the blue, the more CO2, the less O2 is the content. Why is that? Respiration. You have organisms utilizing O2 for respiration. CO2 is a byproduct of respiration. Okay? So here, in this yellow, orangey, and reddish color indicates warm, low nutrient water. That's because the thermocline is a barrier, especially centered around the equator, that really prevents mixing, so you can't get nutrients into the photic zone for photosynthesis to take place. Okay? Oh, there's one other thing I wanted to point out to you. See how the arrows go this way and this way? This is the North Atlantic deep water upwelling in what's called the Antarctic divergence zone. So that's about right here. This is like the subantarctic front. This will be over on the polar front here. But this is the divergence zone, the Antarctic divergence zone. This upwelling of nutrients is what fuels this ecosystem. Why you have all the tonnage of krill and all the baleen whales and so forth down there. Okay. So, adding a little more complexity. Okay. And again, this black line is supposed to represent the thermocline. Once again, North Atlantic deep water moving about. Right? And so we see here these light blue arrows represent volume transport. Okay? The white arrow, but outlined in blue, represents deep water formation. So this represents the deep water formation off the Antarctic coast. That becomes the Antarctic bottom water. This is North Atlantic. Okay. A couple little things of sea ice here. The black arrows are wind-driven upwelling wind. So you have wind blowing across here. It's helping in part what we call a fetch. So it helps to move the water side, and it helps in the upwelling process because it's moving water about. You got to fill in the space. But also, this is also upwelling the fact that as the North Atlantic deep water moves about, it's interacting with these other water masses. When they interact, there's a little bit of friction going on. The friction imparts heat, which means that the density starts decreasing. So the water becomes lighter and it upwells. So that's another factor. Wind-driven upwelling, the effects can only be felt so far down on the water column. Usually at most a couple of 100 meters. We're talking 4 to 6 kilometers deep in the Atlantic Ocean. Now, look at these little red arrows. The red arrows represent, the squiggly arrows represent heat fluxes. So look at this here. Oh, no surprise here. The ocean is going to absorb a lot of heat energy at the equator. So that is no surprise there. But we see what? Because of water holds so much heat, a specific heat of water is very high. So it gives off the heat to the atmosphere here and here. The oceans moving about to the poles will have heat that it contains in this water will flux to the atmosphere. The little green squiggly arrows represent freshwater fluxes. In other words, we see fresh water leaving the ocean. In other words, this is evaporation. So now you're putting fresh water in the atmosphere. You have the same quantity of salt, but less water volume. You're going to do what? You're going to actually make the surface water a little denser. But because the water temperature is so much so very high, it's not going to sink all that much. It's going to stay in the pretty much the upper layers. It's still not going to really be able to entrain any nutrients in here. The green squiggly arrows pointing down represents precipitation. So think of, water evaporates, it travels this way and comes back down as rain. Evaporates, travels this way, and comes back down in some form of precipitation. Okay? Now, when you see these, here it kind of looks like a pair of eyeballs, but when you see a circle with a dot in the middle, what you're doing, this could be either for wind or for a current. But what this represents is that it is current or wind coming straight at you. If you see a circle with a little X in it, then that is flow away from you. So think of like this is the tip of the arrow and it's coming right for your noggin. Okay. Or if you see an X, that's the feathers on the back end of the arrow going away from you. So this is very typical. You'll see this in a lot of diagrams, showing which way the wind and or currents are moving, coming towards you, going away from you. I discussed a lot of that in my rotating systems video as well. Okay. So now we're going to start introducing some, more complexity to this. Once again, the Antarctic bottom water, the Antarctic intermediate water. Here's that warm surface Atlantic water. Here's the North Atlantic deep water. Here's the Mediterranean water. Now you notice there's some branches that moves a little south, and then it starts to upwell and get entrained in the Antarctic intermediate water. But notice this branch right here. This kind of a significant branch. Notice what it's aiming at. Oh, about 60 or so degrees north latitude. This Mediterranean water exits Gibraltar, Coriolis acts upon it, and basically sends it on a beeline right to the Fram Strait. We know the Mediterranean water is getting very, very warm. We know that. And it's taking that heat and ramming it right through Fram into the Arctic Ocean. And that's why we're having the quote-unquote, along with mixing with some Atlantic water, but why we get the Atlantification of the Arctic Ocean, why the Barents Sea basically now has properties more akin to the North Atlantic than to the Arctic Ocean. And we're seeing the same thing happening to the Kara Sea. And soon after that will be the Laptev and finally the East Siberian Sea. So the heat contained in the Mediterranean water makes a beeline through Fram, brings that heat into the Arctic Ocean. It melts the ice early in the year. It prevents or delays the formation of ice later in the year, so you have a longer open water season, more heat fluxes to the atmosphere, and so forth. And now to show you as an example of running a transect, seen this little insert panel, we run a transect like so, and from this transect, we create such a figure. So from this transect, we're dropping the CTDs, okay? Here they're also measuring phosphate, so we're probably taking samples and measuring the phosphate. I'm not going to, that's not it's not germane to our discussion here. But, so here's the transect from which they created this. In this case, this is a 2D representation of this ocean here. So think of this diagram as like a curtain. Okay? And it goes from 0 to 5,000 meters or 5 kilometers deep. Now, Antarctic intermediate water, we see this very distinct tongue here. We see this surface water here. And these values here, 34.6, 35.2, 35.4, these are salinity values. And you see what? In this case here, the halocline bends to the surface. Here's the North Atlantic deep water, Antarctic bottom water, filling it all out. This red dot corresponds to that red dot, the Bermuda Rise. Now, you all heard about, North Atlantic deep water. Well, the North Atlantic deep water is actually comprised of other smaller water masses that contribute to the entire thing. So, for example, we have the LSW. The LSW is the Labrador seawater. Right? Then you have the ISOW and the DSOW. Okay, the ISOW is the Iceland-Scotland overflow water, right? Presumably Scotland, right? And then the DSOW is the Denmark Strait overflow water. And as you can see, the DSOW is slightly more dense, so it sinks a little further deeper. But as you can see, the LSW, the ISOW, DSOW all eventually combine to form the collective North Atlantic deep water. And as you can see here, they're representing it basically from about 1,500 meters down to 4,000 meters, 3,500 meters or so. So this illustrates, water masses coming together. Now flip your brain around. The North Pole is on the left side, South Pole is on the right side. Subtropical convergence. Subtropical convergence, equator in between. Oh, that's because typically in the middle of the big oceans, Atlantic, Indian, Pacific, you have a gyra, and typically in the middle of the gyra is a convergence zone. And in the middle of the convergence zone, you have a downwelling. And that's what these arrows represent. This is representing a downwelling. So you have a gyre forming here. Okay? This M is the Mediterranean water. You see some of it moves this way to interact with the Antarctic intermediate water, but you see a noticeable portion heading towards Fram Strait. So here is the Antarctic intermediate water. Here's the Antarctic bottom water. Okay, some of these little eddies I mentioned earlier. Here's that, as they follow these arrows from the North Atlantic deep water moving up, right? See this right to here? That's the Antarctic divergence. This is the Antarctic polar frontal zone. It represents Antarctica. So what's this here? What's water mass is that? Well, if you saw my previous video about, ice shelves and water masses affecting the ice shelves, you know the answer already. And we see it again here. Now, this is nice because now we get to see a bit of a 3D representation of the ocean. So once again, we're seeing the signal from the Mediterranean water, North Atlantic deep water. Here's your bottom water over here. Okay. Here's the Antarctic intermediate water. We got some surface water and so forth. Now we can start looking at some actual values. So for the Mediterranean water, okay, they're saying 10C and a salinity of 35.5 practical salinity units, PSU. Okay. Now look at the North Atlantic deep water. The salinity is less, 34.9. But it's considerably colder, 2 to 4C. So taken together, that makes this water mass more dense, so it sinks below. And this water mass is more dense than the surface water, so it sinks below that. Now, the water, based on its density characteristics, will sink to where its buoyant forces are counteracted. It finds its own buoyancy level based on density. So for the Antarctic intermediate water, we see 34.4 salinity with a 5C temperature. Okay? So it makes sense that it is less saline and it's also a little warmer, so it's going to be less dense then the North Atlantic deep water, and it will sit over the top of that. But then what is this in between, sitting at 34.6 and 2C? Same thing over here. What's going on? And you see how it seems to be two different water masses here. Okay, I think the suspension is long enough. This is the this here in the lighter shading. That's the upper circumpolar deep water. This is the lower circumpolar deep water. We have some other surface waters here. Now, these little purple dots, I guess, whatever, they represent surface divergence, right? As I showed you in this previous slide, right, the North Atlantic deep water upwelling creates a divergence, and that shows here. So we have water moving apart. These pink, is that? Represents surface convergence. Right, so you got a surface convergence in North Atlantic due to the different water masses meeting up, and the currents as well. And surface convergence, oh, that's the middle of the gyra. Oh, middle of the gyra. And because you have a divergence here, you're pushing water this way, and you got water moving this way, you form another surface convergence. This is actually the polar front, subpolar front. So you get these divergence and convergence, and these arrows represent. In this case, looks like surface currents. Yeah, this would be looks like part of the Antarctic circumpolar current. So you get an idea of 3D representation there, and this shows it even a little more pronounced, a little better detail. Right, see the upwelling going on here. Here's the Mediterranean making its way towards Fram. The yellow is more surface convergence. The orange is divergence. And the reason why you have a divergence off the coast, that's Ekman upwelling. So you have Ekman pumping taking place. So the water diverges off the coast there. So there's the subantarctic front. There's the Antarctic front, also called the polar front. Okay. So in the previous slide, right, that's the subantarctic front. That's the polar front or Antarctic front, and the polar divergence. And and again, we see the upper circumpolar deep water and the lower circumpolar deep water. And they show you some values here, right? 34.9 parts, 2 to 4C, 35.5 parts, etc., etc. So you can see how, and you can look this up. You can take these values and you can go right to the TS diagram, and you can see exactly what these values, what density that gives you. And then that helps you, say, oh yeah, that's more dense than this, so it's going to sink down below it. Or that's less dense, so it's going to ride over it. You can actually take these values, read it off your TS diagram, and get your density. Very straightforward, very simple. Getting the data is another deal. Okay, deep Atlantic circulation. And now a slide that introduces to you the circumpolar water. Again, Mediterranean water, North Atlantic intermediate. There is a North Atlantic intermediate water. It's quickly entrains with the Antarctic intermediate water. We have South Central Atlantic water right here, North Central Atlantic water here, Subantarctic water. Here's the Antarctic convergence, divergence, and so forth. Antarctic bottom water. But now we can see we're indicating the circumpolar deep water, which has been indicated here. Outward flow in one layer and northward flow below with vertical motion at either ends called AMOC. Right? Cool. Southward flow, northward flow. Northward flow. The Antarctic bottom water actually fill in a lot of the deep ocean, the abyssal area. Yeah. And now we see we're identifying the upper circumpolar deep water and the circumpolar deep water. Here's your upwelling, right? Ekman transport, right? subantarctic front, subtropical front, polar front, right? This is the Antarctic circumpolar current front, etc. Little outgassing of CO2, and so on. Now, what's really interesting is that and they should probably have an L here for the lower circumpolar deep water, but the lower circumpolar deep water is the combination of Antarctic bottom water and North Atlantic bottom water, right? Those masses meet. There's a modification, and that modification results in a different salinity and temperature regime. For example, okay, we see, the salinity changes, as does the temperature. As it interacts, as these two water masses interact, they start forming the lower circumpolar deep water. What's interesting about the upper circumpolar deep water is that this is actually the combination of waters from the Pacific and Indian Oceans. To take the deep waters from the Pacific and deep waters from the Indian Ocean, it combined, and the density becomes that it's less dense and sits over the lower circumpolar deep water. So the lower circumpolar deep water is the result of Antarctic bottom water and North Atlantic deep water primarily. The upper circumpolar deep water is primarily the result of Indian and Pacific deep waters. And it is the heat content contained in the Pacific Ocean and to a certain extent the Indian Ocean that is then that gets entrained in this upper circumpolar deep water that then makes its way to the underside of the ice shelves and is increasing the melt rate. So that huge heat blob that I described for you in my ocean heat content videos, that huge heat blob that's basically filling in practically all of the Pacific Ocean, especially the North Pacific Ocean, down to very deep in the water column. That heat is making its way to the underside of the ice shelves and melting them. So this shows it a little better, more of it 3D. This yellow arrow here, that's the Antarctic circumpolar current moving in this direction. And notice we have what? Now they finally identified. Lower circumpolar deep water. You see how that sits in between the North Atlantic deep water and the Antarctic bottom water. Whereas the upper circumpolar deep water is less dense, and so it starts riding above the North Atlantic deep water. But it's still more dense than the Antarctic intermediate water, which is found here. This is surface waters. This is some examples of little pinch-off eddies. We got some heat fluxion going on. PF is polar front. Okay? So, again, going back to this, okay, this where we start seeing the upper circumpolar deep water sitting above the North Atlantic deep water, but underneath the Antarctic intermediate water. So it's right here. There's your UCDW. There's your LCDW. And just another diagram showing you some of the the little eddies that can pinch off and circulate, forming little cells here. Circumpolar deep water making its way up and bringing that heat to the underside of the shelves. Okay. It's showing you east wind drift, circumpolar current, polar front divergence, etc. Okay. This is just a diagram showing, just reinforcing what we've been discussing to this point here. And of course, you guys can always pause the video to look at any of these diagrams in further detail as you so may desire to do so. But yeah. So now we can briefly talk about Pacific and Indian Oceans. Pacific Ocean has a less complex stratification weakly layered, displays sluggish circulation, and is remarkably uniform below 2,000 meters. Okay, notice we see the influence, yes, of the Antarctic intermediate water making its way into not only the Atlantic Ocean, but both the Pacific and the Indian Ocean. NPIW is North Pacific Intermediate Water. This is just, Pacific water of the deep water here. SPCW is the South Pacific Central Water. NPCW is North Pacific Central Water. COW is simply common water. No, it's just just common water. It's like one big thing, whole bunch of water masses just contribute to this. So when they say it's remarkably uniform, it's because this is common water. The properties are pretty much the same throughout. Not much happening. Where the Pacific water, the deep water meets the common water here, we get a little interface here, a little entrainment and mixing and so forth. Same thing with the North Pacific Intermediate water meeting the Antarctic Intermediate water, a little bit of mixing, entrainment, etc. But keep in mind, it is the heat that is found here that makes up part of the UCW that goes over to here. This is sea ice, but imagine you having the ice shelves here. So you take the heat, wrong way, taking the heat from here, it goes here, melts the ice. Same thing here, heat from the Indian Ocean, but bigger contributor from the Pacific. Indian Ocean has the simplest stratification, consisting of common water, Antarctic Intermediate water, and Red Sea Intermediate water. That's RSIW, Red Sea Intermediate water. Here are your common surface water here. Okay? Antarctic Intermediate water, those are central water. This is your central waters, and this is your common water. So South Indian central water, East central water. And it's pretty not very exciting, unlike the Atlantic, and they get pretty uniform characteristics throughout the depth. And now, we'll talk about the Arctic Ocean. You got the Bering Strait on this side, the Fram Strait on this side. You have ice. You have a polar mix layer, so that could be freshwater input, from precipitation, river, that kind of stuff there. Okay? You have the Pacific halocline and the Atlantic halocline. The Pacific halocline, because the Pacific Ocean generally is less saline than the Atlantic Ocean, which is more saline, the density is going to be slightly less. So the Pacific halocline will ride over the top of the Atlantic halocline. In fact, you can see the signature going right this way. This is the Pacific halocline. Now, keep in mind that the halocline is constantly changing, especially as the seasons change. So it's a very dynamic situation, and there's a lot of work being shown how the halocline is changing, how it's getting shallower, how the mixed layer is being affected, etc. But we see the surface water here. Here's the Atlantic layer. So when the water comes in through Fram, some depending on the density, some of it will be, up in the upper 200 meters or so. Some of it sinks down, where the heat will eventually flux its way upward. Okay? So we have, Atlantic water, Pacific water, etc. Then we have the deep water. And these values here, 25 years, 30 years, 75 years, that's what we call resident time. In other words, the number of years it would take to flush this. If a parcel of water moving in until it gets replenished or flushed out and recycled and replaced takes about 25 years on the Atlantic side, about 30 years on the Pacific side. And when you get into the deep basins, 300 years, because it's very dense water and it takes a lot to what we call ventilate it. So it takes a lot to push that water out. Lomonosov Ridge, etc. And to create this diagram, here's the transect where they took the measurements to obtain this result. This is just showing it a little more detail for the upper layers. So the Pacific halocline, right? The Atlantic halocline, right? And then the deep water, etc. Again, there's your transect. How the sea ice gets affected affects what the sea ice does affects the halocline. Forming the sea ice affects the halocline. When you don't have a sea ice there, what does precipitation, riverine input? How does that influence and affect the halocline? It's very dynamic and it's constantly changing from just seasonality alone. For a small region, it's quite a dynamic situation, quite a dynamic place there. Okay, now I'm sure you're all familiar with this. This is this nice little ribbon-looking thing, or tapeworm, anyway. But this little ribbon thing here, you have warm surface flow, cool subsurface flow. This is supposed to represent the conveyor belt. Now, if we followed the conveyor belt from the formation in the North Atlantic, right? Iceland, so on. We'll call it the Greenland, Icelandic, Norwegian Sea. It's where it tends to form. This is where you get the Denmark Strait, the Iceland overflow water, the Labrador surface water. This is where all those contribute to the North Atlantic deep water, all feeding into this here. It sinks, right? Gives off its heat, gets cold, very dense, very salty to begin with, and it drops, right? So you have your deep water formation here, right? And travels down. A branch goes into the Indian Ocean, upwells, gets warm again, and then returns as a surface flow. Another branch continues flowing, outside the Antarctic continent, goes into the Pacific, upwells, right? And travels back this way, hooks up with this flow, and returns here. Of course, part of it returns into the Gulf and entrains the Gulf of Mexico, where it picks up the Gulf Stream, etc. Very simplified, but it gives you an idea of it. A quick note here, when we talked about the previous slide of the Eastern Central Water, South Indian Central Water, okay, South Indian Central Water here, Eastern Central Water here. If one were to follow a parcel of water right here in North Atlantic, as it sinks, it travels about and returns, on average, of course, it's going to be varying times depending on its precise route. On average, it takes about 570 years to make the loop. On average. Some cases it can be up to 1,000 years. Again, water masses are moving, but they're moving slowly. Diffusion, etc. But they're still moving. They're still distributing heat, CO2, oxygen, nutrients, etc. Okay. Another thing to note here. You see how if you look at the Pacific, you look at the Indian Ocean, very large basins, right? But look at the Atlantic. Okay. You have the Mid-Atlantic Ridge that runs up the middle of this. The Atlantic Ocean is really a big rift zone. You have plates pushing apart, pushing North America and South America away from Africa and the Eurasian landmass, pushing it apart. Because the Atlantic Ocean, it started out as a crack, and so it's gotten wider and wider over the millions of years. But if it's going this way and this way, what do you think is something has to give, right? So the Pacific Ocean is actually getting smaller. And you got all those plates that literally ring around, the Ring of Fire. So you got a lot of deep subduction zones. Pacific plates being pushed down into the mantle. So the Atlantic Ocean is getting bigger. Pacific Ocean is getting smaller. Now, I've seen estimates that the Atlantic Ocean is spreading at about the rate of 1 or 2 centimeters a year, something like that. So after a century, it's like a meter or two. May not sound like much, but that's a bit. So just keep that in mind. The Atlantic Ocean is really just one big rift area. Now this is kind of I just kind of tossed this in here. Gives you like a kind of a quick aspect of the 3D nature of the conveyor belt. It sinks down to depth, it comes up to the surface, right, and then it returns as a surface flow. So just to give you an idea of how much not only horizontal distance it covers, but vertical distance it covers. And as it's moving about, it's all water is mixing. It is all mixing. And this fusion, double diffusion, thermohaline flow. And, one other thing I want to mention is when we see, something like this here, right? Like the Antarctic intermediate water, the common water here. This is going to be like a density interface here. And you can get internal waves that can propagate along these density interfaces here. Same thing up here, same thing over here. And these propagation can also distribute faster materials, heat, CO2, O2, nutrients, so forth. So internal waves, can propagate. And as they propagate, they'll move faster than the water mass itself that can be tooting along sluggishly. And that can help speed up the distribution of, you fill in the blank. So keep that in mind as well. That's what I was referring to when I mentioned the density, the internal waves at the density interfaces. Yeah. And of course, like everything else, you could get little pinch-offs. And those little pinch-offs can enhance mixing as well as distribution. Okay, so what's going on here? Well, this is looking at the butt end of the planet. Looking at Antarctica here, right? And we see what? The purple represents deep water formation. So here's the deep water formation in North Atlantic, right? Here's the deep water formation off the coast of Antarctica. You get the little bit of upwelling in the Pacific and the Indian Oceans. So you get a deep water formation. The red is the surface current. The blue is the deep current. So this blue that you see around Antarctica, that's your circumpolar deep water. Oh, you see how the Pacific feeds into that? You see how the Indian Ocean feeds into that? As well as the Atlantic waters feed into that. See that? All feeding into, and then it separates into the upper and lower. But there, you can see how it feeds into the circumpolar deep water. And this red circle that you see here, surface flow, that's your Antarctic circumpolar current. And you can see you got some stuff feeding into it, branching off, and so forth. Which leads me to this. Here you go. Now, you can pause the video if you want to see what all the different acronyms stand for, like RSW's Red Sea Water, right, et cetera, et cetera. So we got the Atlantic Ocean here, the Indian Ocean here, Pacific Ocean here. So we've got some the blue dotted line here, that's the Antarctic circumpolar surface current. Here's your circumpolar deep water, this green here. And then we have SAMW is subantarctic mode water. That's right here. Okay. Along with the lower intermediate water, the LOIW, which, by the way, one of these earlier figures here, SAMW, that's South Atlantic modified water. That's kind of what you're trying to get to here. But what I want you to, the takeaway message from this chart here is that think of what goes on around Antarctica, right? All these flows around Antarctica. Surface, the intermediate levels, at deeper levels. Think of this as one big rotating hub where you got waters feeding into it, waters feeding out of it. Right? Feeding in, feeding out, feeding in, feeding out. In other words, what goes on in the Southern Ocean connects every other ocean. All the oceans are connected. Eventually, in some manner or form, all the different water masses will interact with each other. This big hub drives it. This drives it all. Think of this like the Grand Central of the oceans. Right? All the train stations, right? All the trains coming in and leaving. This is a big hub that connects all the oceans, connecting all the water masses, helping to move all the water masses about. Water masses feed in, water masses feed out. And this shows it. Right, from the Pacific, from the Indian, from this side, Indonesia, right? It all ties in together. Circumpolar deep water, right, comes off of it, feeds into it. Everything ties in. Antarctic bottom water, filling in the Atlantic basin. You can see North Atlantic deep water, the gradual arrow, right, upwelling at the divergence zone. And they're giving some, for example, the upper intermediate water, they're given a density range of 26.8 to about 27.2, or 1,026.8 kilograms per cubic meter to 1,027.2 kilograms per cubic meter, and then 27.2 to 27.5 for the lower intermediate one. They just threw in a couple of values just to throw it in there, but that's how you would look at that. So that's, I think this shows it a little more dramatically, because this is a 3D representation, which is more of a 2D representation. But that is the complexity. It gives you an idea of the complexity of what's going on, how what goes on in the Southern Ocean is really connecting all the oceans. So to give you as an example of what's happening, with the situation in the North Atlantic. Typically, when you had a very hot Gulf Stream moving up, typically you brought heat from low latitudes to high latitude. It gives off the heat, helps modify the higher latitudes. And at the same time, you bring the cold temps to from the high latitudes to the lower latitude to help cool down the lower latitude. So in other words, all this oceanic water mass movements, surface currents, deep water flows, etc., everything is basically the conveyor belt, right? Is a big heat distribution mechanism for the planet. So typically, you have the warm Gulf Stream gives off this heat, indicated by these little red arrows fluxing. It's very salty to begin with. It cools down, becomes very dense, and whoop, goes southward. That's your deep water formation. Notice the relative thickness and darkness of the arrow, indicating that it's a lot of it and a lot of it's flowing southward. Here's the Antarctic intermediate water flowing northward, Antarctic bottom water flowing northward. Okay? Ocean water cools, becomes denser, forms a powerful deep southward current. What happened before during the ice ages? Well, Gulf Stream wasn't as hot, wasn't moving as fast, less heat fluxing to the atmosphere. You can see the ice sheets grew. So instead of the water sinking to deep depths, it only sank to intermediate depths. And it spreads without filling the deep Atlantic. And you see how the arrow is not as thick, not as wide. The blue coloration is a little less blue. You see it kind of peters out when you get to about, off of South America, whatever. But you see what? You see that the Antarctic bottom water fills in, right, has to fill in the space, so it fills in more of this. So the Antarctic bottom water becomes more prominent, reaches further into the North Atlantic. So in the past, when this has happened, the planet, at least hemispherically, went into an ice age because the heat distribution mechanism was no longer there. If you had asked me 6-7 years ago, would I think global warming will lead to an ice age? I would most likely have answered yes, because of this mechanism. Because we have data that tells us this has happened before. AMOC slows down or stops, we get an ice age, where the ice sheets grew. AMOC kicks up again, we get in between the ice sheets and the ice ages. Right? I no longer subscribe to that. And the reason I no longer subscribe to that is because of the massive heat content in the oceans. So, yes, AMOC is slowing down, and we're measuring it. What I think will happen is that you'll get regional cooling, so that the northern eastern seaboard of North America and Scandinavia, northwestern Europe, the UK islands, what have you, Iceland, they will cool down. Their weather will be a little more snottier. It'll be a little cooler, a little colder to deal with, maybe more snow and precipitation form. So, but I don't see, because of all that ocean heat content, I don't see at least hemispheric cooling. I just don't see that happening. You can see your waters from the south fill more of the deep Atlantic. That's that Antarctic bottom water. So, remember, it is the oceans that are the main climate drivers or driver. I guess ocean plural. Okay. Though the atmosphere plays an important role, the oceans are the main drivers. This is due to the specific heat capacity. Specific heat of water is a hell of a lot higher than air, as well as the storage, right? Ocean heat content, along with the high latent heat content, right? Latent heat energy, in wintertime, walk along a river where there's some open water, and you see what looks like a little foggy thing on the surface of the water. That's because the water is warmer than the air. It's giving off its latent heat energy to the atmosphere, and you get that foggy effect. So, and remember, since 1971, approximately 93% of all the energy we have introduced to the atmosphere, heat energy, due to burning of fossil fuels, has ended up in the oceans. So only 7% is creating all the havoc we're seeing with, precipitation bombs, atmospheric rivers, all the stuff of recent days and months and so forth. Well, with the increased heat in the ocean, we're seeing increased stratification. So the heat is no longer being sequestered to depth effectively, or if at all. Therefore, that heat is staying in the upper layers. And thermodynamics informs us that it will flux, it will diffuse to the atmosphere, heating up the atmosphere. Even if you assume just say 30% of that heat energy in the oceans fluxes to the atmosphere, that will be sufficient to cause a 3 to 4 C increase in atmospheric average temperatures, in which case we're screwed. Okay? And what heat doesn't flux to the atmosphere will go and melt the ice. So then you start melting the ice. Now the question becomes, okay, so you introduce all this melt water. Will that not cool down sea surface temperature? The answer is yes. But you then have to conduct your heat budget. What's the volume? What's the heat capacity? What's the joule content? And then compare that with the rest of the oceans. I think you will find that the heat content in the rest of the ocean will be greater than any cooling effect contained in the ice. So let's say, ice raises, if all the ice, Greenland, Antarctica melts at once, okay, sea levels, rise, what are they saying, up to 75 meters or so, okay? Well, how deep are the oceans? How deep does the heat content go? In other words, and don't forget, you put in all that, it's fresh water, so you're not going to it's going to be cold and it's going to be salty and start sinking. No, it's fresh water, so the density is still going to be lighter, it's still going to float, but you now have the stratification from below it, the heat will flux upward. In my view, it will warm up any melt water that happens. Couple that with the trapping of the CO2 as the water temperature increases before all this meltwater gets introduced, you're going to have CO2 outgassing, increasing the heat holding capacity of the atmosphere to further warm up the air. So while melting ice sheets will cool down sea surface temperature, it's what lurks underneath to the hundreds of meters below that, even thousands or 2,000 meters below that, that heat will, in my view, diffuse upward and warm up those waters. So you may see slight modification of sea surface temperature, but do not expect a massive or drastic decrease in sea surface temperature. So that's kind of what I'm getting at with this here. Okay, we are now seeing this huge heat capacity at work in the events occurring around the planet in recent months and years. Also important is the fact that the oceans and atmosphere are really a coupled integrated system. But remember, it is the oceans that are the main climate drivers. So, if you found this video informative, please give it a thumbs up. It helps with the algorithms for my channel. It helps promote my channel. If you are not already a subscriber, please subscribe. Please share my video, this one and my other videos on your whatever social media you utilize. And if you are not a patron on my Patreon, I hope if you are able to, I would greatly appreciate it if you could help support the work I do by becoming a patron over at patreon.com. And you'll find the details in the description box below this video. So there you have it. Just wanted to kind of, I won't say quickly because you can spend courses on ocean water masses, but I want to at least bring you this, somewhat in-depth introduction to water masses, and I hope that you get an idea and appreciation for what water masses are, what controls how they move about, and basically the density, which is based on temperature and salinity, and also the fact that due to what takes, especially what goes on in the Southern Ocean, that they're all connected. Everything is connected, and they all communicate with each other. And the circulation that you see at the bottom of the planet is a big hub that just brings in all the water masses, lets them enter, lets them exit, but everything is connected and driving this climate system we call planet Earth. Thank you for your time, and I look forward to speaking with you again.